everyone. So today I'll be talking to you about transparent transaction ordering and blockchain-based collaborative processes. So let's break the title. So starting with the very basic blocks and what is basically a collaborative process. It's a process between multiple participants who are trying to achieve a goal. This goal could be a business goal or any other type of goal. And so to describe this process, we can use choreography diagrams, and these are part of BPMN. It's a descriptive language to describe processes. So this is one of the basic block of this choreography model language. And this is a choreography task or message, and we can see participant A and participant B. What's happening here is participant A being the sender, sending a message to the participant B, which is below. Of course, we can have also a sequence flow between multiple messages. So here what happens, we start with the event, A send a message to B, and then B reply with a second message in the second task. It could get more complex with logical gateways. And here, for example, we have an XOR gateway where we can examine a condition, basically just like if else. And if this condition is satisfied, we take the first branch. If not, we take the second branch. So here, for example, B is sending a different message depending on the condition. Now, where exactly the process state is handled, we can first we can have supposing we have a lot of participants here, not just A and B. We have more than 2 participants. So where do we handle the process state? We could go with a centric solution. For example, here we take B as a central point where they control the entire process state. Or we can distribute it among all the participants. So we have partial states between participants. And in this case, we have a lot of blind spots in the process. We don't know exactly what happened. Not every participant is fully aware of what's happening in the process. So they have to ask each other and they have to trust each other sometimes. What we can also do is to use a blockchain technology, which offer us this solution to have logically it's centered, but physically it's distributed among all the participants, with the data is replicated, and we can also ensure immutability of the data. So now the process state is shared among all of the participants, and thanks to the blockchain, we can assure that the data is replicated equally among all the participants. Now, how does this work? It's a different story for a different time, but most importantly, you've heard of proof of work, proof of stake. These are consensus protocols that ensure that the data is replicated correctly and no one can alter the data or modify the data as they wish. Now, what do? In this topic is basically we take this process and deploy it on the blockchain. How do we deploy it on the blockchain? We compile it to code, and this code is what you've heard probably about is smart contracts. So smart contracts are executable code on the blockchain. And so we compile the process into smart contracts, and then we deploy it on the blockchain. And now participants can interact with each other in this process through the blockchain by sending transactions. So each message is basically a transaction on the blockchain. Everybody can see this transaction, and it's immutable. You can't reverse it. Once it's there, it's always there. Now we will have this simple example throughout the presentation, and it's a simple supply chain where a customer is placing an order for the store, and then we check if there's enough supplies. Where do we check if there's enough supplies? On the blockchain. There's a certain quantity on the blockchain, and we check the state of the supplies over there. If there's no supplies, we reject the order. If there is, the store send the details to the logistic provider, the delivery party. And then we have event-based gateway. This is different from the logical gateway. Here, there's no condition. Basically, the first message that happens is taken, and the other is rejected. So if the logistic provider confirmed the shipping first, the customer can't cancel the order anymore, and vice versa also. And yeah, it keeps going until the process ends. Okay. So how does this happen? What happens behind the scene on the blockchain? Let's take this example, the first task, placing an order. So the customer sends a transaction to the store, and this transaction contains the necessary information for the order, placed in something called mempool or transaction pool, which is something still not on the blockchain. It stays there until the miner takes the transaction and adds it to the block. When it's added to the block, it's propagated among all the participants, and all the participants are aware of this transaction. Now, there could be a lot of transaction pools. It's not only one. And yeah. So what's the problem with this is based on the miner. So the miner is selected based on the consensus protocol. And most of the time it's based on it's probabilistic. And the miner, when it's selected, has the full advantage of selecting whatever transaction they want to add in the block. So this is a bit of a disadvantage of the blockchain when it comes to the ordering of transactions. Since we don't have a central point, it's up to the miner how to select the transactions. So what can they do? They can perform front-running attacks. Probably some of you have heard of it. For example, they can swap the position of the transactions. Unlike how it is in the mempool, they can also suppress it. They can remove it totally, censor some other transactions. And you can see how this can affect the process. Any participants in the process selected as a miner, they can manipulate the ordering of the transaction to their own personal gain. So back to the example, where does this front-running attack occur in the process? So when the customer places an order to the store, we might have multiple instances of this process running at the same time. So we can have multiple customers competing for limited supplies from one store. And this is prone to this type of attack. So if a customer was selected as miner, they can for sure censor the transaction of the other customer. We also have it within instance. So here, as I said before, the first transaction that is taken or the task is taken and the other is canceled. So the customer can censor the logistic provider transaction, which is confirming the shipping, or vice versa also. So let's see this into details. So starting, as I said, with two customers placing an order. First, they send the transaction to the transaction pool. They wait there until the miner takes the transaction and add them to the block. So for the sake of this example, let's assume that we have one mempool and we know what's in there exactly. So first, transaction 1 is before transaction 2. Now, supposing customer 2 was chosen as the miner, they can easily put their transaction first, canceling the transaction of customer 1. And in this case, supposing we had one supply, customer 2 will get the supply and customer 2 will get nothing. Across the instance is also the same thing. So here the customer was selected as the miner. They can cancel transaction of the logistic provider, and then the logistic provider can't confirm the shipping, but the shipping is canceled. So the final state is we have order as canceled. Now, what's the problem here is that the task is when the transaction is sent directly to the blockchain, and we don't know exactly who the miner will be selected. It's totally random. It's not something that we know how it is selected, and the miner has the full advantage of ordering the transactions however they want. So what do we do is so this is how it happens from the process directly to the contract that handle the process. What do we do is we have we add middle stages where we can buffer the transactions first, and then we can select the miner, and here we call them the orderer, however we like to select them, and basically we select them based on the choreography, based on the state of the process. So they're not randomly selected. Now they're based on they're context-based selected. So now we have a middle contract, which is called the ordering contract, which stands in the middle. And this is where we select the orderers, and this is where we order the transactions before submitting them to the main process contract. So let's see how this works. Go back to the first example where the customer trying to suppress the other customer voice. And now instead of having one transaction, we have meta transactions. Meta transactions aren't executed directly on the blockchain, but are kept. We buffer them and then we execute them later. So these meta transactions only include the metadata that the customer wants to execute later. So now what we have is we don't take it directly. We have buffering, and we chose to have 2 blocks of buffering. Now, as we can see, customer 1 transaction was suppressed in the first block, but in the second block, we could send it again because the consensus protocol, we can't have a miner selected for 2 subsequent blocks. And so now at the end, we have the 2 meta transactions for the customer 1 and customer 2. Now, how do we select the order? We have 2 questions to ask: who will select the order and how to order them? And to do that, we extract what we have as meta transaction and draw this simple node graph. So we have the 2 customers sending the transactions to the store to order a supply. And what we chose is to choose the intermediate node. So here we chose store as the intermediate node will be responsible for ordering the transactions. Of course, there could be multiple strategies to do that, but we thought of this as being the most neutral party to select the transactions, as there's no competition between the store and the customers, but the competition is between the customers themselves. Now, just for the sake of expanding the example, let's supposing we had the second store. What do we do now? We choose the intermediate node. So store 1 and customer 2. Customer 2 can only order these transactions, and MTX2 and MTX3, and store can order MTX1 and MTX2. There could be also different strategy. We can select all of them as orders, and we can, for example, select someone who's outside the circle of these transactions. But for us, for now, we just selected the intermediate node. So now what the store does is they send their OTX, is the ordering transaction, which includes the orders they wish to have. And so here the store chose to have MTX1 over MTX2. So the transaction of customer 1 over customer 2. And in this case, customer 1 will get the supply. Even though customer 2 tried to suppress the transaction of customer 1. Yeah, so this entire process is we call it an epoch. So we have multiple epochs, and then inside the epochs, we have the buffering, as I described it, and we have the ordering phase and the execution phase. Now, in this case, the entire epoch took 3 blocks. It could take more based on the complexity of the ordering. We could have multiple orderers, and this could take time to take place. Now, how do we evaluate our work? Of course, we take the 2 instances here, the cross instance and within instance, and we deploy this on the blockchain and execute it. And when we executed, we designated two participants as being malicious nodes. So those nodes perform the front-running attacks. We chose customer 1 and logistic provider 2 being the malicious node. Yeah. This is what we get. So in the plain setup, without our proposed approach, we can see how customer one, being the malicious node, obtaining all the supplies. And with our solution, we chose for the store to distribute the supplies evenly. Of course, it could have been different, but this is what we simulated. And we can see that, of course, because the store was choosing, both of them got equal amount of supplies at the end. Also for within the instance, we can see how logistics provider could confirm most of the orders. With the ordering contract, we could make them look more even. Now the performance, of course, this has increased the time because we had more steps to do. And for the cost, for the transaction cost, of course, it also increased because we had multiple transactions to be sent to achieve this ordering. And this is it.